Hello guys, so this is question 3 from the ladder problems. Let's start. A ladder of negligible weight is propped against a rough vertical wall. Again, when it says a rough vertical wall, that means we have a specific mu value for the wall. The coefficients of friction being the same at the wall and the ground. So we know that mu is the same for the wall and the ground. So we have the same mu, alright? Mu is equal for both. The top of the ladder is 10 meters and above the ground, and the bottom is 6 meters from the base. So we are given our vertical height, so which is the top of the ladder is 10 meters above the ground. That is our vertical height. Okay, so we have this 10 meters above the ground as our vertical height, and the bottom is 6 meters from the base of the wall, meaning this is our horizontal length. If a man climbs the ladder, find the minimum value of the coefficient of friction. So we need to find our mu value so that he reaches the top of the ladder before slip takes place. So there's a few important concepts here. First of all, it says a ladder of negligible weight. So we do not have any weight of the ladder. We only have the weight of the man. All right. So the weight of the ladder is not important. And it is saying that the man is reaching the top of the ladder. So his weight is going to be at the very top of the ladder, which is at the top of the wall. And this is before slip takes place, meaning that all our case is all still in equilibrium and there is no motion. So let us start by drawing this. So this is our wall. This is our ground. And this is our ladder. Okay, so what do we know? We know that this height, this is 10 meters from here to here. So this is 10 meters. And we know that this is 6 meters because this is already given in the question. The 10 meters above the ground and bottom is 6 meters from the base of the wall. All right, so this is our wall and this is the ground. And this is our ladder in purple. The ladder will not have a weight in the middle because the ladder is assumed to be weightless, but we have the weight of the man, which is at the very top of the wall here. All right, so we're gonna have the weight of the man here, W. Okay, this W is the weight of the man, so W is weight of man, not the ladder, because the ladder is weightless or assumed to be. Now let's look at our forces on the ladder. We have our normal force here, and we'll call this N1. And we have our friction force over here as well. We remember this ladder is going to slip downwards, so our friction force is going to be upwards. So we'll call this FR1. And for the bottom of the ladder, we have the same thing. We have a normal force going up. So we'll call this N2. And remember, if this ladder is slipping, it's going to slip to the right, and friction is opposite to motion, so friction is going to be to the left. All right, so this is our friction force 2. And remember that mu is equal for both the wall and the ladder. So mu here is equal to the mu here. All right, mu is equal to the mu of wall equal to the mu of ground. All right, so this is our case that we have over here. And let us just from now assume our positive directions. This is our plus x and this is our plus y. Okay, first step always is your friction force equation, which is FR1 is equal to mu times N1. Okay, we don't have any of these values, so we can leave it like this for now. And so this will be our equation 1. And the same thing we can do for the bottom, which is FR2 is equal to mu N2. All right, again, this is the same mu. This is the same value of mu because they have the same coefficient of frictions. And this is equal, this is our second equation. So now if we move on, let us do our sigma of x and sigma of y. So sigma fx equal 0. All right, what is our sigma of x? We have N1 going to the right, which is positive. So sigma of x is equal to positive N1, positive N1. And we have friction going to the left, so negative FR2. And this is equal to 0. So we can find our third equation now, which is N1. FR2 will take it to the other side, is equal to FR2. This is equation 3. Alright? We will do exactly the same thing again for sigma Fy. So let me just take this over here. Copy this down here and make it smaller. And we're going to do our Fy again. So sigma Fy equals 0. Our sigma Fy is upwards is positive. We have plus FR1. We have plus N2. Then we have minus W, which is going down and equal to 0. So we can write our fourth equation as W is equal to FR1 plus N2. Alright? So this is our fourth equation. These are the easy equations that you usually get out. Now let's look at our moments. Alright? Let's look at our moments. Let's bring this a bit more down. And let's talk about moments. So sigma moment is about a point is equal to 0. Alright? Which point do we have? We have 2 points. We have the point, well, let's call this point 1 over here, the blue. This is point number 1, which is the point of N1 FR1. And we have point 2, which is the point N2 FR2. Okay? So we can choose any of these points to find. Let's analyze it first before choosing. So if we use a 1, we're going to cancel out all these forces. We will be left with only N2 and FR2, which is not enough because we need a moment that has the weight in it. Because we have an equation with weight and we want to cancel out weight. So if we get the moment of FR2 and N2 by themselves, we're not going to get enough equations to solve this problem. So we need this variable to be a part of it. So we actually cannot choose point 1 because the weight is acting on it as well. Since the weight is acting on it, there's no perpendicular distance. We will not get our W in our equation. Therefore, we have to choose point 2 so that we have a perpendicular distance for the W and we can solve it. So that is why we're going to choose point 2, not point 1. Here, it is very direct. We are already given our perpendicular, our distances here. We do not have to do any trigonometry to find it. So let us just apply our equation. So the first thing we have is W. All right. W times a perpendicular distance. What's the perpendicular distance for W over here? If I increase the size of this just a little bit, so we can look at this. So W, if we are extending this force to the bottom, you will notice that this distance here is their perpendicular distance to point 2. So it is our 6 meters. All right. So 6 meters is our perpendicular distance. The same thing can be said about FR1 because if we extend the force, it is acting at the same place. So if we extend the force here, you will notice that FR1 is also our perpendicular distance to FR2 or 2.2, I should say. Okay, so 6 meters is also for FR2. So plus FR2 or FR1, sorry, times 6 meters. Or actually, we don't know if it's plus or minus yet. Let's just keep this. We'll look at the signs later. And then we have N1. N1. The perpendicular distance for N1 is now not the same 6 meters. We have to look at what forms a perpendicular with the force. So here, this is the perpendicular distance. All right. So if you notice, N1, the perpendicular is already formed with this line over here, which is, let me do it in green, with this vertical line. Because this vertical line is forming a perpendicular with the force, and it is the distance from point 2. You can look at it in a different way as well. If we move this up here a bit. if we're extending the force, all right, if we're extending the force, you'll notice that we have a perpendicular distance over here, which is equal in size to the left. This is our perpendicular distance to point 2. Okay, so it's the same distance over here, which is 10 meters. So times 10 meters, and this is all going to be equal to 0. Now let's look at direction. So first thing, we're going to look at W. If we draw a line from the tip, the arrowhead of W to the point, you're going to notice it is going into that direction. All right, so this is counterclockwise, so it is negative. Again, I am assuming my clockwise is positive. All right, so I'm assuming clockwise is positive. Clockwise, positive. Okay, so this is counterclockwise, so it is negative. So I know my W is negative. Same thing I'm going to do with FR1. FR1 is clockwise, so it is positive. So this is plus. Same thing I'm going to do with N1. Again, it is going into this direction, so it is positive. So clockwise, so it is positive. And now we have our final equation, equation 5. Let us simplify equation 5. We're going to see that FR1, we're going to keep 6W on one side. All right, so we're just moving it to the other side, and is equal to FR1, or 6FR1, plus 10 N1. Okay, this is just if I'm rearranging and simplifying this equation, moving 6W to the other side, we're going to have 6W is equal to FR1 plus 10 N1. And this is our equation 5. Okay, this is our simplified equation 5. Now we're going to take all the equations that we have had so we can solve. So we have equations 1 and 2 over here. We have equation 3 over here. We have equation 4 over here, and equation 5 at the very end, which we found using equation 4 we found using sigma Fy, equation 3 we found using sigma Fx, and 1 and 2 we found using the friction rules, and now equation 5, which we used the sigma moment to find. Again, the way to substitute is always make sure you are getting rid of all your frictions and having everything in terms of N1. So first thing I'm going to look at is I'm going to look at these two, because we have here N1 is equal to FR2. So I'm going to put this N1 instead of FR2. So it's going to become N1 is equal to mu N2. Okay, this is from combining equations 2 and 3. Using this, let's plug again. Let's plug N1 into the N1 in the very beginning over here. So we're going to get FR1 is equal to mu N2. Sorry, it's going to be mu times mu again N2. Why? Because this is N1. N1 is equal to mu N2. So we're just substituting this in terms of mu N2. That's it. All right. So all I did was I put this N1 over here, and we got this. All right. This is all I did. Now we have FR1 in terms of N2. We have N1 in terms of N2. That's great. Let's look at equation 4. We have FR1 and we have N2. So we already have an equation FR1 in terms of N2 that we can substitute in this. So for W, for this equation, we can put W is equal to, instead of FR1, I can put mu. All right. If we just simplify this equation a bit more, it's going to become mu squared N2. All right. This is mu squared N2. Mu squared N N2, N is green, N2. Okay. So this is mu squared N2, mu squared N2, which is simply just FR1. FR1 is equal to mu squared N2. That's what we are substituting here. So again, we are just putting this FR1. We're substituting it here. That's all we are doing, which is mu squared n2. So it's this, all right? That's it, that's all we are doing. With mu squared n2, what is remaining? Plus n2. All right? So we just simplified this equation. Now we have w in terms of mu squared and n2. And now we have our final equation over here, which is 6w is equal to fr1 plus n1. So we have an equation, we can substitute n2 into this equation. Like we have a formula for w in terms of just n2. We have a formula of fr1 in terms of n2. And we have a formula of n1 in terms of n2. So we're going to plug all of these now into equation 5. And it will look something like this. So instead of w, we're going to put mu squared n2 plus n2. All right? That's what we're going to substitute for this w. For this fr, we're going to substitute this first equation, which is just mu squared n2. So mu squared n2. And n1 is just mu n2. All right? So it is mu n2. So let's plug all of these in now. So it's going to be 6 times mu squared n2 plus n2. Okay. And then we have the equal sign. And then we have 6 mu squared n2 mu squared n2. Just going to put these in boxes so you guys know that this is just me plugging in, substituting the values. So mu squared n2. The last one is going to be plus 10 plus 10 n1. N1 is mu n2. So mu n2. And now we have an equation like this. Let's do ourselves a favor and just take n2 is common out everywhere. So we can cancel it out easily. So we're going to have 6 n2 times. Remember, if we're taking n2 common from here, we're going to be remaining with mu. All right, we're going to be remaining with mu squared. Plus, when we take n2 common, n2 by n2 is just going to be 1. All right. To check what I did here, just redistribute and you will see that all I did was I took the common factor n2 out. Same thing here, we're going to take 6 n2 out times what will be remaining inside is just mu squared here plus 10 n2. What will be remaining inside is just mu. Okay? If you notice here now, we can divide both sides of the equation. We can divide both sides of the equation by n2. And n2 will just cancel out. Alright? So anything you do to the left, you do to the right. So we're dividing both sides with n2. And you will notice these n2 will just cancel out. Okay? And that's it. Because remember, when we're dividing by n2 like this, it's the same way as saying this over n2 and this over n2. It's the same meaning, okay? So they're all cancelling out. So what we will remain with is 6 mu squared plus 6, if I just distribute the 6 inside, all right, is equal to 6 mu squared plus 10 mu. If you notice, we have a quadratic equation. So we're just going to take everything to one side. We're going to have, actually, if you notice, if we take everything to one side, it's going to be 6 mu squared plus 6 minus 6 mu squared minus 10 mu equal 0. All right, so all I did was I took this to the other side. So they become minus and minus. Here, if you notice, 6 mu squared minus 6 mu squared becomes 0. So all that we are remaining with is 6 minus 10 mu is equal to 0. So if we take it to the other side again, so 6 is equal to 10 mu. That means our mu is equal to 6 over 10, which is 0.6. And that's how you would solve question 3.